Good morning, students. I hope everyone's doing well. Um, Enjoying the cool weather. Again, I know I always talk about the weather, but it's it's remarkable again to live in a place where we enjoy such nice weather. And uh, except when it's raining, but uh, I'm grateful. I just wish my nose didn't itch so much, but that's fine. Uh, I'm happy that I can get up in the morning and run and enjoy the beautiful scenery that we have on this great planet. So what I want to do today is go back to the idea that we started with the Taylor polynomial and give a little bit more detail into that theorem. That is a major result in real analysis. It's not to be taken lightly. It's like the geometric series or the Pythagorean theorem. If we didn't have it, we'd have to invent it. So I want to say more about that and then do some more examples and get you acquainted with the remainder term, which we need to talk about. And so after that, we'll conclude that, and that'll be pretty much most of the lecture. And then I want to introduce the power series, which will be a natural transition from the Taylor polynomial. So just like I told my pre-calculus students yesterday, I hope you're enjoying this. Now you're kind of seeing how all that hard work is starting to pay off, because now we're seeing that the calculus that we've been doing has just really been an exercise in, as they say, sophisticated arithmetic. And that's what we do. That's what we do in calculus. And I think everyone thinks it's just some magical cantation that we do. It's just arithmetic. So let me share my screen. And I got pretty lucky here. I didn't really adjust this document cam very well. Let me move it down a little bit and over. I have to be careful. When we first started the class, I was telling one of your classmates that I had the document cam over too far and I dislocated my shoulder. And I thought, well, that's not good. I need to be able to write. So I'm a little bit more careful about how I position it. So what I did, ladies and gentlemen, is I started out with this calculation just to kind of give you some detail into how we come up with this rather odd looking formula for the Taylor polynomial. And then we'll show that it's actually valid. So what I want you to do, I started this calculation so you would kind of see where I was going, and we'll finish it. We're going to use the same notation for Taylor polynomial. And you know, when C is 0, we call it Maclaurin, just if that comes up. So if we think about a polynomial of degree n with just the standard coefficients from pre-calculus, this is what it would look like. So we would have a constant term and then a1 times x minus c to the first power plus a2 x minus c to the second power. So this would be a polynomial with expansion point c, or centered at c. That's how we think of these types of Taylor polynomials. That's what they look like. And so, like I said yesterday, they're n plus one points where there needs to be agreement. And the points have to do with the function and all of its n derivatives. And I mentioned that last lecture, but I'm sure it probably didn't ring very true. But I was being honest with you. So I want to now elaborate as to why I said that, and then maybe go into the detail about why this polynomial actually is going to work for us. So what I did first is I want the agreement between the polynomial and f with no derivative at c to agree. So the beauty of this calculation is that it's kind of like a telescoping series. All the terms pretty much go away. So notice here, when you evaluate the polynomial at c, all of these terms absorb. They just have 0 factors in them. So the only thing that's left is a sub 0. So what I've done here, and I started to erase, and then I said, no, I'll do it. I'm just going to put a 0 factorial there. We know 0 factorial by definition is 1. So I'm just going to stick it there as like a placeholder. Okay, now what I want to do, I want to make sure we have agreement for all the derivatives too. So first, again, taking the derivative of a polynomial, I know this is kind of dry, but it's going to help you understand this and maybe help you believe this theorem. We take the first derivative. So of course this is 0, so we just use the power rule here. Notice we just get 1 here and then the 0 power. So this just gives us a1 times 1, which we have here. And then this term will give us 2 times a2 times x minus c to the first power. Now the beauty of all of this is that when you think about the chain rule and all, the derivative of x minus c is just 1. So we don't have a whole lot of issue here when we differentiate. We really have an easy time of it. So basically what happens is that we just have the power rule, 3 comes down, then we have a 2, and then of course the derivative of the inner function is 1, and then we just toggle down to the very last one, and we have n times a sub n times x minus c to the n minus 1. So these derivatives are, it's like doing the integration by parts. We have an easy derivative, and then we need to have an easy integral for it to work. Now we want agreement. So we want f prime of c to equal the derivative of the polynomial at c. But again, notice when we evaluate at c, all of these terms absorb because we just get c minus c. And then we're left with a sub 1. Now I'm going to do the same thing I did before. I'm just going to multiply by 1 factorial. You know, these formulas had factorials in them, so I'm going to go ahead and introduce them, even though now they just look like placeholders. 1 factorial, of course, is 1. So let's do this again. And now I think you'll see a pattern. Let me shift this over a little bit. Let me shift the, here we go. Modern technology still has old-fashioned technology. There we go. So we'll get this. Let's go ahead and differentiate again. So we're going to differentiate this function. So that'll be a 0. So now we get the 1 times the 2. So this will just be 2 times a 1, a sub 2, and then of course to the 0 power. So we just, that goes away, derivative just being 1. And now plus 3 times 2, a sub 3, and then we have x minus 1 to the first power, and then of course the derivative of the inside is 1, so we're done. And now here again, chain rule, we have n times n minus 1, a sub n, x minus c to the n minus 2, and of course inner function derivative is just 1. So now you're seeing why I've been doing this factorial bit. So now we want agreement at the second derivative when we evaluate at c. And of course now all of these terms, oh, sorry, I don't know why I made that into a 1. I was thinking the power 1. Of course, math is just so good to us. It tells us when we make typos, and we are human, but that's why I'm training you to write all of your work out so that you can find the mistake and fix it. So now when we evaluate at c, that's a 0. All of these are 0. That's a 0. And we're just left with this term here, which now I'm going to write as a sub 2 times 2 factorial. Okay, now I'm going to do the third, and then we're just going to jump down to the nth because I think you're seeing a pattern now. So let's do the third derivative of the polynomial. We'll just use a 3 here. So now we look at this, that of course is 0. So now we have 3 times 2 times 1, a sub 3. And then of course to the 0 power, that just being x minus c, derivative is 1. So we just, you know, just kind of playing the symbolic dance here. And then of course, the next term I don't have, but I can just go ahead and write it down. It's going to be a 4. In this case, if we mirror this, a 4 times a 3. and that would be times a 2, and we would have an a sub 4 x minus c to the first power. And then as we bump on down, again, we'll get the n minus 2. So we have n times n minus 1 times n minus 2 a sub n, and then we have x minus c to the n minus 3. So again, we're just doing the derivative game. The derivatives aren't too complicated. And now we want the agreement at the third derivatives when we evaluate at c. Again, the n plus 1 points. So now, of course, no, all of these terms with the x minus c absorb, and we're just left with this. So this will be p sub n 3 at c, which will now just give us a sub 3 times 3 factorial. So this is an inductive argument, basically, an inductive argument where we see that each step depends on the previous step. So now, with this pattern, we can see now that when we're done with all of this, the nth derivative here will just be the n factorial times the a sub n. That'll be the only thing that's left. So think about it as moving in an inductive pattern. And by the time we've taken this many derivatives, the only thing that's left is just that one power. So let me write this down like I did like this. This will be n times n minus 1 times n minus 2 to, I'll just put these in parentheses, and then 1, and then a sub n. And so the nth derivative at c will just be a sub n times n factorial. So this is what I mean when the n factorial started to come into the mix. Now, of course, if this were an infinite series, when we talk about the Taylor series, then we'll have extra terms out here like we do here that'll clearly all go to 0 because they'll have the x minus c in them. So this argument will come back up again, but we won't have to do it again. We're doing it here. So now we see that in general, so this implies, or equivalently, for all of these n's, so we take the order of the derivative. Here the order of the derivative is 0. Here the order of the derivative is 1. Here the order of the derivative is 2. Here the order of the derivative is 3. And then I can't say, well, I won't say n equal n. I'll just say nth derivative. You're thinking maybe we could use k as our index variable. And I can do that if you like. So now we can say in general, if we just solve for the coefficient, we just divide the nth derivative by n factorial. And that's what you saw in the Taylor coefficients. So it's exactly what's going on. So now we see that a sub k will equal f sub k, that is the superscript k for derivative at c divided by k factorial, where k runs from what? 0 to n. So of course, when k is equal to n, we just get the nth derivative at c divided by n factorial. When k is equal to 0, we just get the 0 derivative, that is f of c divided by 0 factorial, which is f of c. So we like our definition of factorial to help us in the extreme cases so that we don't get division by 0. So there's a reason we make those definitions. So these coefficients here that we see for the Taylor polynomial are just basically a common sense argument that says if we want this polynomial to agree with this function that has n derivatives, you know, remember it's Cn on the interval a to b, that it has n continuous derivatives, we must have this even if everything else just blew up and didn't work at all. This would have to be the case, regardless of the argument that we were dealing with. So in order to do this, you can see that the hypothesis of Cn is extremely important. We need derivatives to exist, and we need them to be continuous. We can't have infinite discontinuities running around in this argument. That's not going to work. So again, now when you look at the Taylor polynomial, for instance, remember what we said. We said now the Taylor polynomial looks just like this. Let me remind you what we got for it. We'll just have f of c right here. A sub 0 is f of c plus f prime of c divided by 1 factorial. We just leave that out, x minus c. So now we're just filling in the a0 up here. And then plus f double prime of c divided by 2 factorial times x minus c squared. Now, of course, we'll just bump up to the nth one. And then the very last one here will be the nth derivative evaluated at c divided by n factorial x minus c to the n. Now, that's the Taylor polynomial. And I like the way Dr. Larson mentions this. It's like, okay, so what? Well, that's good. So is it any good? Can we depend on this? And so the Taylor's theorem went one step beyond this. That is, we found that for some z, for every x in the interval a to b where c lives, there's going to be, for every x, there's going to be a z between x and c such that, and I'll say that again, such that we can replace the function f of x with the Taylor polynomial and then shore it up, so to speak, with the remainder term. That is, there'll be a term that will fill in the gap, so to speak. And what did that look like? Well, we had the remainder term had the z in it. This would be the n plus first derivative. So we need the n plus first derivative to exist. Evaluated at z divided by n plus 1 factorial times x minus c to the n plus 1. So that kind of put the nail in the coffin, so to speak, to say, okay, well, if this is going to be any good, we just need to know that we can control this, or that we have some way of knowing how much of the gap is there. Can we make it small? Can we control it so that if we do replace the function with the polynomial, is it going to be any good for us? Because we've already started computing them. So let's talk about that. So again, now hopefully these coefficients aren't very mysterious, and you see that it's a really common sense argument to get them. Now let's go into a little bit more detail. Now, like I said before, what we want to do is apply Rawls' theorem. So here's what I'm going to do. We're going to start, and this argument's not very difficult, but we get to do another telescoping example. And I know you like telescoping because it's easy. So we have fix, and I'll start this argument, fix x and c in the interval a to b, which we call I. And now that we know what the polynomial looks like, we're going to say that the remainder is just equal to the function f of x minus this polynomial that we determined just now what it has to look like. So we're going to say that, and then for t element of I, we're going to define some function that basically looks like this, and then apply Rawls' theorem to it and get the remainder term based on what I just wrote from the Taylor's theorem. So here's what the function looks like. So we're going to call it a function of t. So first, and this is interesting, we're going to say f of x, and this is how you think about it. You just subtract the polynomial. but you replace the c with the t. So we have minus f of t minus f prime of t times x minus t. This is ingenious. I mean, this is not a unique function. It's just like proving the mean value theorem. You just have to come up with something that works, and then boom, you make it. So minus the second derivative at t divided by 2 factorial x minus t squared, and I'll write the third one, f triple prime at t divided by 3 factorial x minus t cubed, and then we'll just bump down to the very last one, and then the remainder type looking term. And then we have minus the nth derivative at t divided by n factorial and x minus t to the n. And then this term here that utilizes the remainder with an x minus t factor to the n plus 1 divided by an x minus c factor to the n plus 1. Now, the thing is that Taylor came up with this theorem. He probably did some experimentation with the mathematics and said, well, here's the theorem, and I'm going to use it. But unfortunately, in most cases, mathematicians would come up with a theorem that they would have no idea how to prove it. They said, well, this makes sense. And I've used it and it seems to be working, but that's not a proof. So mathematicians that followed him come up with the proofs, and they validate. It's like validating Ramanujan or validating Sir Isaac Newton. You know, you fill in the details if they didn't bother to do the proof. Maybe they just saw the theorem in their head and boom, they just wrote it down and said, oh, this is correct. But they're like, I know it's right, but then they say, I'm not going to bother with a proof. So we have to fill in the details. So notice this nice theorem here, this nice function here is a nice function. Why? Because f is Cn. It's continuous because f is continuous, and it's differentiable because f is Cn. So we can say this. Let's see, how do I want to write this? Yeah, by hypothesis on f, g is continuous. We're going to look at the x and c. G is continuous on the interval, and the closed. Remember, we need closed for the continuity and open for the differentiability. On the closed interval determined by x and c. Remember, we don't know the order of it, so we just say x and c. And g is differentiable. It has derivatives. It's differentiable on the open interval. On the open interval. Oh, I don't need to write it twice. Determined by x and c. So that's really good. We get two of the hypotheses of Rawls' theorem very easily, just by the fact that f is such a nice function. Now, remember, with Rawls' theorem, you have to have 2 points on the curve, namely the x and the c, that correspond in terms of their output. That is, we need to show that g of x equals g of c. And then, since it's differentiable, it must have at least one horizontal tangent. And that's the key to the theorem. So now what's my favorite word? Observe. That's what I use in pre-cal. They're still not used to it. We have to observe the math, and what's going on before we can move to the next step. That's the problem with my pre-cal kids. They don't always observe. So let's observe that. Let's look at this. It doesn't matter which order. I think the first order that I did here, let's see, I completely rewrote my notes here to make it more user friendly. Let's just start with g of x. So now we put in x for t. Remember, this is a function of t. So g of x means replace all the t's with x. So we'll do the easy one first. So this is f of x minus f of x minus f prime of x times x minus x. So we're getting kind of like the polynomial bit. All of these terms are going to zero out. Minus f double prime of x divided by 2 factorial, x minus x squared minus third derivative, x 3 factorial, x minus x to the third, and bump on down. Again, replace t with x n factorial, and of course we have x minus x to the n, and then minus the remainder. So we get x minus x to the n plus 1 divided by x minus c to the n plus 1. So this is the easy one. Notice all of these terms here have the x minus x. So they zero out or absorb, obviously. And then, of course, these just absorb in the standard way that Professor Ron says. So that equals 0. So if and only if g of x equals 0. Now we need to use how we defined the remainder to get the second part. So we're going to use this in the second part. Now g of c. So everywhere we have a t, we're going to replace it with c. But it's just going to mimic the Taylor polynomial. So this somewhat, this particular polynomial is new to me. I've seen and constructed other proofs of this, but I think this is ingenious because it's so straightforward. So we have f of x minus f of c minus f prime of c, x minus c. So this is just mimicking the Taylor polynomial. F double prime, again, of c, 2 factorial, x minus c squared. And then I'll just bump on down. We know what that's going to look like. So then minus the nth derivative at c divided by n factorial, x minus c to the n, and then minus Rn of x. And then, of course, the x minus c here, the t replaced with c, this term fraction will just give us a 1. So that was ingenious how this function was defined. So now notice we just have the Taylor polynomial with the negative sign and the remainder, because that term right here, that factor is 1. So if and only if we have g of c equals f of x minus, and again, the part here is just the Taylor polynomial, and the part here is just the remainder. And by how we've set up our proof, this is just 0. That is f of x here, when we transpose to the other side, this is just the definition that we have for f. So this is identically 0. Now that's good and fine, but we still need to know precisely what R is. And that's now what we can do. So now we see with these very simple calculations, and when I say simple, they are simple, but the key is coming up with the function that'll work. And again, the function's not unique. Rawls' theorem is very general. It just says find a function that has these hypotheses hypotheses, and then you have this horizontal tangent. So you come up with a function that gets you where you want to go. Otherwise, raw doesn't have anything to do with it. They just like, it's a very flexible theorem. So now, with all of this satisfied, that is, we have continuity, we have differentiability, and we have the two outputs equal, we have at least one horizontal tangent. So write this down, by Rawls' theorem, and this is where we get the z. By Rawls' theorem, there exists z between x and c such that, and this is very important, g prime of z, that is, at z, we get a horizontal tangent. So that's the key, and this is going to give us the remainder. So this is the key step. The interesting thing about infinite series, the way I teach it, is that you know what an infinite series is. It's a sequence of partial sums. You know the integral test, you know the comparison test, the alternating series test, you know the geometric series test. And now you're going to know why Taylor's theorem is actually an arithmetic result that is of emphasis of such magnitude that without it, again, we'd have to come up with something else to fill its place, because it is the reason that we have calculators. The arithmetic to run the calculators is right here. So now your little magic box that you probably paid too much money for, you know why it works. And for instance, we're going to keep adding to this, and then you future computer science majors can enjoy doing some numerical analytic techniques with these ideas. So what's next? Okay, so let's look at it. We just need to do this. All right, so what I'm going to do is we're going to take the derivative, but I've got the function right up here, and we're going to differentiate it. So I'm going to cover the part up we don't need. So this part right here, so I'm going to adjust this so you can see the function. We just need to take the derivative of it, and we're going to find out that it telescopes, and we're going to have what, two surviving terms. So let me just, cover up what we don't need. And then we're going to evaluate it at z, and we'll have our remainder, and we'll be done. And then we'll do some examples using these ideas now that maybe you will believe them. So now, compute g prime of t. Now this just takes a little bit more work, but it's very simple. And then we'll have to notice a pattern. So g prime of t, remember x and c are fixed, so x is a constant. So that's a 0 right there. When we differentiate that, we're done. Remember, x and c are fixed. I wrote it on the previous page. So now when we take the derivative, we get minus, excuse me, f prime of t. This is in the abstract. We know we've got all kinds of derivatives of f through order n plus 1. So we get f prime, we're done with that term. Now we've got the little dot here, so we've got the product rule. So we get minus f double prime, take the derivative of f prime, we get f double prime, times x minus t. And now we leave this alone and take the derivative here. But notice we've got a negative. So we've got -1. So basically at this point, we just get negative. So we get plus f prime of t. So when we think about these derivatives, we have to now use the chain rule because we're differentiating with respect to t. And that's going to produce, in many cases, a negative, which gives us a positive. Okay, so now when we take your red pen, we've done this, we've taken care of that. Now notice you see that these two terms will absorb. And that's going to be the case until we get to the very end of it, and we're going to have a couple of surviving terms. Now, let's look at this one. Let me leave this pen here so I can get to it. So now we're going to take the derivative, again, product rule. So this will be minus f triple prime of t divided by 2 factorial times, excuse me, x minus t squared. And now we leave the first part alone and we bring the 2 down. So here we notice when we multiply in this case and bring the 2 down, it's going to absorb the 2 there in the denominator, the factorial. And then of course, by the chain rule, we get another negative. So that will absorb that negative. So this will give us plus f double prime of t, in this case, times x minus t, which will now absorb that term. So let me just review here. When we take the derivative here, we bring the 2 down, it absorbs the 2 here, so we have a 1. And then the derivative of the inside is -1, negative, negative, positive. So now these 2 will absorb. So we've done this one, check. Now let's go to the next one. So again, product rule, we have minus, so we take the derivative of this term, we get the 4th derivative in the abstract. And then we have an x minus t to the 3rd. Now notice when we take the derivative of this term, the same thing happens. When we bring the 3 down, it absorbs the 3 and we're left with 2 factorial. And then the negative here from the chain rule absorbs that. So this gives us plus 3rd derivative, leave the first term alone, but the denominator is changed to 2 factorial. And we have x minus t squared, absorb. So you see the pattern? That it's at first it's a little bit hard to look at these derivatives that we have to take, but that's where the pattern is. So we're getting absorb, absorb, absorb. Okay, so we keep going. So we got minus, plus, dot, dot, dot. We go to this term here. So again, do the same thing. So we're going to have minus the n plus first derivative of t divided by n factorial times x minus t to the n. Okay, same song and dance. And now we leave this alone. Remember, the n will come down, kill one of the factors of n in the n factorial, and then the negative here by the chain rule absorbs that negative. So we get plus nth derivative of t n minus 1 factorial x minus t to the n minus 1. Now this will absorb in the previous set of terms. And now we're going to see, okay, so what's left? So we can see now that this n plus first derivative will never have a counter. There's no other n plus first derivative that we're going to have in these calculations. So this term survives. This one absorbs because it's in the previous calculation with the minus sign. And so we can see absorb, absorb, etc. So this derivative, lo and behold, is telescoping. Now for the last one, that's the easy one. Notice in this particular case, the Rn of x, that's a function of x, that's a number because x is fixed, so we don't worry about that. So we just take the derivative of this. So now we get the n plus 1 coming down. So we get, and then of course the derivative of the inside is -1, so that absorbs this. So we get plus Rn of x divided by n plus 1. Let me not make that fraction bar so long. Times x minus t to the n divided by x minus c to the n plus 1. And of course, there's no other term like this, so I think you'll believe, if you haven't believed anything, you know this survives, okay? So the idea, I'm chuckling because we've done this so many times. By now, I think you get telescoping some. It is a huge mathematical abstraction that we believe in and that we need. And without, this would be a nightmare, absolute nightmare. Okay, so when we take the derivative, ladies and gentlemen, these are the only two terms that survive. And then we can evaluate it at z, and then we've got what we need. So well, let me do this, check, right? So now, remember, we need to do this. So let's write down the derivative that we have. So I tried to set up this so you could see the function as we differentiated it. So if and only if g prime of t equals these two terms. So we have the negative of the n plus first derivative of f at t divided by n factorial times x minus t to the n plus Rn of x divided by n plus 1 times x minus t to the n divided by x minus c to the n plus 1. Now, when you look at this and you say, okay, so what do I do here? Well, let's go back to this. Here's the z. So we evaluate g prime at z and set it equal to 0. And that will give us the formula for R. So now, well, g prime of z equals 0. So we have g prime of z equals 0. So let's replace, in this case, t with z. So we get negative f n plus 1 of z divided by n factorial times x minus z to the n plus Rn of x divided by n plus 1 times x minus z to the n divided by x minus c to the n plus 1. Now, of course, these are equal and opposite, so we'll just flip them around. So if and only if Rn of x divided by n plus 1 times x minus z to the n divided by x minus c to the n plus 1 equals f n plus first derivative evaluated at z divided by n factorial times x minus z to the n. So now these guys absorb. These absorb. And now what do we have left? Well, notice that all absorbs, and if we solve for the remainder term, we divide, or excuse me, we multiply. Let's see. I've got my n. Did I put my? Oh. Here's a. How funny. Let me see here. Let me check something here. We got the, yeah. Here we go. Where did I put my derivative? Yeah, right here. Let's see. I've got one thing I want to check. Let's see. I did g prime, and then we did the derivative. Oh, notice here. When I do the n plus 1, take the derivative of this, that's just a factor n plus 1. It doesn't go into the denominator. For some reason, I put it in the denominator, so forgive me. So here, when we take this derivative, and so we've got this part And let's see here, this n plus 1 is times, not in the denominator. So, because when it comes down, it's just times n plus 1. My bad. That looked kind of odd. So every place here, this is times n plus 1. That's just bringing the power down. I got into the routine of dividing. So Professor Ron, so we have an n plus 1. So make that change. I think I fixed it in all the places where I did it. So now notice when we solve for Rn, the remainder term, now we divide by n plus 1. That gives us the n factorial. So n plus 1 times n factorial is n plus 1 factorial by definition. And then we have the n plus first derivative evaluated at z. And then we multiply by x minus c to the n plus 1. And we are done. So yeah, when you take the derivative at this point here, remember when you take the derivative of this, the n plus 1 just comes down to the coefficient. And I stuck it in the denominator, which was a brain freeze. So push up the n plus 1 here. And so now when you solve for the remainder, we got this. And then when we go back to the original part of our theorem, let's see, right here, we've got it. That is, f of x is indeed the Taylor polynomial plus the remainder, and the remainder looks just like that, where z is between x and c. See, that this is what's neat about these theorems. When you work them out, you really do exercise what you know about Calculus 1. That's all we've been doing in this class is Cal 1. I've just taught you how to use the Cal 1 with these new objects. And so we just do Cal 1 and a whole lot of pre-Cal. I showed the kids yesterday how they're going to do trig sub in Cal 2. And they were like, oh, that's so easy. Well, of course, bless their hearts. I hope they think that way when they get to Cal 2. Hopefully I'll have prepared them for it. So maybe that's a blessing in disguise. So what we see here is that now when we had this theorem stated, you can go back to the statement of the theorem, and now it makes sense. That is Taylor's theorem. That is, we have a natural number and we have a interval a to b. Suppose f has continuous derivatives through order n on an interval I containing c, and the n plus first derivative exists. Then for any x and I, there exists a z between c and x such that this is true. The Taylor polynomial plus the remainder, and boom, that's what the remainder looks like. And that's the configuration, a possible configuration of the c, the z, and the x. So I was not lying to you, but it is important to have the n plus 1 times not in the denominator so that our remainder theorem comes out okay. So I want you to understand this. I want you to know the components of this proof. This is like the fundamental theorem of calculus in Calculus 1. And ladies and gentlemen, if you do not know that proof, you need to learn it. That is a standard proof for any calculus student, honors class, non-honors class, San Jacinto College, Texas A&M University, MIT, Harvard. It's the same thing everywhere. Calculus is calculus. So you can kind of consider this the fundamental theorem of calculus for Calculus 2. This is a monumental result, and it shapes your ability to do calculus from here and evermore, okay? So now that I've preached about the importance of it, let's do some examples. Do some more examples. So this again, I don't like to just throw out some result and say, oh, all right, kids, believe this is all it is. I want to show you that you have the knowledge and you have the structure from your previous class to do it. I haven't used anything in this theorem proof that you didn't learn in your previous classes. So the idea is that now you can appreciate what we're doing and see that the result is justified. So now let's look at an example where we just compute, let's see what I want to do. Let's just compute another Taylor polynomial just to remind ourselves what we've been doing. And let's do a one with a logarithm. But before I do that one, what I want to do is remind you of the Taylor polynomial for cosine. It's like the sine, and then the e to the x. And we're gonna take c equals 0. So here are I'll just say good for an example. Let me not call it good. They're all good. Oh, a second. Drop my Wacom pen, and if that gets all crazy, my computer starts doing funny things. Excuse me. Too much junk on my desk. You can tell I'm a math professor. So here we'll say let f of x equal cosine x. And we'll take the expansion point to be 0. So we want a Maclaurin polynomial. Maclaurin polynomial. Now these have nice derivatives like we had before. So I just want to review this. And so let's just do like we did before. Let's do in this case, let's do a degree 4. And then on some of the next ones, we'll actually evaluate the remainder theorem once you get used to doing this again. So let's look at this. So we've got the order of the derivative, and then we have f n of x, and then we have f n evaluated at 0. So the Maclaurin polynomials are real popular. We still do others like that, and we'll do another one of those with a non-zero here. So we have 0, 1, 2, 3, 4. If we're just doing the 4th degree, we'll go through 4. If we need the remainder, we have to bump up to the 5th degree to get the next level there. So here we have cosine x. So cosine of 0 is 1, pre-cal. Then we have negative sine of x. Negative sine of 0 is 0. Then the derivative here, we have the derivative of sine is positive cosine with the negative. So we have negative cosine of 0, which is negative 1. Now the derivative of cosine is negative sine, made negative, is positive sine. And sine of 0 is 0. And of course, the derivative of sine is cosine. So we just go back and forth. You know, this pluses and minuses bit. So cosine of 0 equals 1. So now we want the 4th degree polynomial. And this will just be f of 0 plus, let's just write it down, f prime of 0 x plus f double prime of 0 divided by 2 factorial x squared plus f triple prime of 0 divided by 3 factorial x cubed plus f 4th derivative evaluated to 0 divided by 4 factorial x to the 4th. So let's fill this in. Well, f of 0 is just 1. And then, of course, the next term here, the coefficient is 0, so we just get plus 0 times x. For the next coefficient, we have a negative 1, so we have minus 1 divided by 2 factorial, x squared. And then we have plus, okay, we've got a coefficient, so we have 0 divided by 3 factorial times x to the 3rd. And then for the 4th term, or the 4th degree term, we have plus 1 over 4 factorial times x to the 4th. So now we're thinking, okay, this makes sense because cosine is an even function, so we're developing even powers. Just like odd powers with signs. So we get 1 minus 1/2 x squared. And then, of course, 4 factorial is 24 plus 1 over 24 x to the 4. So the idea here is that you're thinking, well, we can just generate an infinite series from this, and we see the pattern. We see the pattern here. This is just, you know, we can figure out a way to write this and be done with this. This is just factorials of even integers and even power. So we're thinking, can we extend this to infinite series and then replace sine with an infinite series or cosine? So here's the beauty of this. For instance, we know if we're really, really close to 0 and we're doing a physics problem or an engineering problem, if we're in an interval that's small, about 0, we could replace the cosine with 1. That would be a decent approximation, and we'd have to figure out, you know, how close we needed to be so we would know what the error would be. Again, if you recall, the 5th degree for sine x, we got something like this. We got x minus x cubed divided by 6 plus x to the 5th divided by 5 factorial, which is 120. And so now this is no surprise. When x is close to 0, so say just like we had before, we've got 0 and we've got a fairly small interval about 0, then we know that sine x can be replaced with x. Well, we know this is true because we know the limit as x approaches 0 of sine x over x is 1. And now this is starting to make sense. So the thing is that the calculus we've already done is completely consistent with this new mathematics that we're seeing in Taylor's theorem. So the arithmetic of the polynomial, the arithmetic of these powers of x, now transform the abstract nature of the sine and cosine defined on the unit circle to a basic arithmetic property. So we know when we define the cosine of the cosine on the unit circle as the x coordinate of any terminal point, and the sine on the unit circle as the y coordinate of any terminal point, we're introducing an arithmetic, and we understand the arithmetic of the unit circle, and we can get a lot of exact values for sine and cosine. But when you use your fancy calculator, it's utilizing these polynomials to generate excellent decimal approximations. So what is calculus? It is sophisticated arithmetic. That's all it is. And the bonus of the technology is that the computers can add and subtract, multiply and divide really fast. And that's what makes the technology such a boon to us. Now, another couple of things that we want to talk about. There's another function that's really important, and that's e to the x. And we want to look at the Maclaurin polynomial for that. So I want to get some of these simpler ones out of the way so that when we extend them to infinite series, you'll look at them and boom, you'll be like, I got it. I know what this is. So let's look at e to the x, which is our friend that has the easiest derivatives on the planet. And we'll say that we want another Maclaurin. So we'll say Maclaurin polynomial. Let's just say here, we'll do a degree 4 too. So we'll do the same thing, but talk about simple. We'll take it. So now we have n, the nth derivative. Now remember, not all derivatives are this straightforward. So we bask in the joy of having simple derivatives here, but just remember, in some cases you may have to work a little harder, but you know what to do. I mean, the polynomial tells you what the coefficients are. So 0, 1, 2, 3, 4. So we have this is the easiest column in the world, right? E to the x, e to the x, e to the x, e to the x. I kind of like that. Okay, so now we have what e to the 0 by definition is 1. So all of these are 1. So yeah, I mean, we had to work for this a little bit, but this is like the best thing. I mean, one of the most miraculous functions in all of mathematics is the natural exponential. It is the base of calculus. It's just like E is to calculus and real analysis as pi is to geometry. I mean, and then of course the pi and the natural base coincide or conflict with each other in the calculus. So it's amazing that we can enjoy this function that we discovered it or had the sense to find it. So now we can say p to the 4th. Again, let's just write it down. F of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial x squared plus the third derivative at 0 divided by 3 factorial plus the fourth derivative evaluated at 0. And of course, we need a power here. These are all power functions. That's why we talk about power series. We just extend the polynomials to series. And then, of course, as we've learned, that we're going to find that any convergent power series is its Taylor series. So if you determine the power series by a different method, it will be equivalent to the method of using coefficients as we're doing here with Taylor. So every convergent power series will be its Taylor series. So that's going to be a big plus and another huge convenience of the mathematics that we do. So now, so the 4th, just fill it in. F of 0 is 1. And then we get 1 times x. And then we get 1 here. All these are 1. So 1 divided by 2 factorial, which is 2 x squared. 1 divided by 3 factorial, so that's going to be a 6. And then 1 divided by 4 factorial, which is a 24. So now we see we just get 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. So that's going to admit a nice simple formula, which is the power of x divided by the factorial. So this will, like these here, will admit a very simple formula in the Maclaurin series. And you will use these to create other series because within the interval of convergence, the power series will behave like a function, and it'll have all the properties of the function that you enjoy from college algebra. So it's amazing here that some of these functions are very user-friendly. Not every function is going to be as user-friendly as the sine and cosine and the exponential, natural exponential, but what we're going to find is that the geometric series will open the door to new techniques that will actually coincide with this and be quicker. So we're going to have all kinds of neat things to do. So we're going to use this in a problem. Now let's just do an example where we have a different expansion point, then we'll look at some remainders. So here's an example. We're given the function ln of x. You're thinking that's an important function in analysis. So let's look at this. And you're thinking we could probably do some geometric series with this. So there are all these integral formulas, the du over u that defines the log of u. We can use that. I mean, that we're going to have all kinds of methods to utilize your calculus to have different approaches to setting up power series. I think you're going to enjoy it. So now let's take c equal 5 and compute, in this case, the 4th degree Taylor polynomial. So here we've got something besides 0. Of course, 0 wouldn't work anyway. We can't evaluate it something where the function doesn't even exist. So we have to be a little bit more crafty with the natural log. It's not as user friendly, but that's not that's not a surprise, is it? Let me adjust this just a little bit this way so I can, there we go. So now let's do our little table, and we'll just do what, 0 to 4. And these are kind of easy to do. We've got n, we have f, because we can do these derivatives in our head pretty much. The nth derivative, and then we want to evaluate at 5. So long to the 0. This is really important. This topic usually gets shortchanged in Cal 2, and I'm not going to do that. Students say, well, why don't, let's just move on. I'm like, well, you need to get this. So we have 0, 1, 2, 3, 4. Now, let me space these just a little bit more because we've got fractions and we need room for them. So let me not be so cavalier here. So 1, 2, 3, and a 4. So now, what's the original function? Ln of x. So we get ln of 5. So if you like, you can just write, you can do parentheses or just whatever. WebAssign puts the parentheses in for you, but ln of 5 would be fine. And then, of course, we have 1 over x. So now we get 1/5. And now, of course, this is where we start generating the powers of 2. So this is going to be negative 1 x squared. Let's just go ahead and finish these. So this now will bring a negative 2. So we'll get 2, negative, 2 over x to the 3rd. Bring that up, then we'll have a 2 times a negative 3, x to the 4th. So these are easy to do in your head. So, just don't get used to it. Sometimes I just want you to see some computations that are relatively straightforward so that you'll develop some confidence, just like doing the integrals. You start out kind of straightforward and then you branch out and have to be a little bit more careful with your arithmetic. So now at 5, we'll get what, negative 1 over 25. And then 25 times 5, that'll be 2 over 125. And then, of course, 25 times 25 is 625. So these are the values of our derivatives. So again, we want the 4th degree Taylor polynomial. So I'll give a little more room here. This will be f prime of 5, excuse me, f of 5. Good old eraser tape. You all probably don't remember the days of the eraser stuff in the bottle. Tough, better than nothing, but you had to wait for it to dry. Here, Professor Ron just does this and we're good to go. So this is if you become a chemical engineer and you develop something like this, then you have a wonderful life. You'll become a philanthropist because you will hit the jackpot. So this is good stuff. Kind of like the cell phone, as far as I'm concerned. So we have plus, and then we have f prime of 5 divided by 1 factorial times x minus 5. Then plus f double prime of 5 divided by 2 factorial x minus 5 squared plus f triple prime at 5 divided by 3 factorial x minus 5 cubed. And then lastly, plus the 4th derivative evaluated at 5 divided by 4 factorial x minus 5 to the 4th. Now, the reason I'm writing this out, you're thinking, well, Professor Ron, we know this. You've only written it down a million times. But here's the thing, kids. If you don't write this down, you don't really have a guide, and it's so easy to make a mistake. So it's better to write it down and then have something to follow. as opposed to just, okay, I do this and I'm done. Well, it's better to check. So now let's fill everything in. We have log of 5 here. So this is ln of 5. You can do that if you want. And then we have f prime. So we've got minus 1 over 25 times x minus 5. And then the second derivative. Now, sorry, that's a, my goodness. Don't jump down too far too soon. There's f prime right there, so that's plus. Yeah, it's great to have large hands for music, but it's small spaces aren't the best. So we have 1/5 x minus 5. And now for the second derivative here, we've got a negative 1. And then, of course, we have the 25, and then times the 1 over 2. X minus 5 quantity squared. And then move down. Then we have plus 2 over 125 times 3 factorial, that's 1 over 6, x minus 5 cubed. And then for the last term, we have minus 6 over 625. And then, of course, the 4 factorial is 24, so 1 over 24. X minus 5 to the 4. So again, just pair everything off. And if you've got these all stated, just be sure to move down the list correctly. So now what does this give us? So we have ln of 5 plus 1/5 x minus 5. And then, of course, the 25 times the 2, that'll give us a negative 1 over 50. X minus 5 squared. And then, of course, here, if you like, this is just 2, and this is 2 times 3. So that gives us 3 times 125. So that's what, 375? So 1 over 375 x minus 5 cubed. And hallelujah, we got a 6 here, and a 6 times a 4. So the 6 is absorbed. And so that's going to be what, 2,400, and then 4 times 25 is 100. So that gives us 2,500. So now when you look at this, again, this is fancy or sophisticated arithmetic. And so now we're thinking, okay, if we wanted our computer, you know, the logarithm takes a lot of adjustments because the logarithms don't converge as quickly. And so your calculators have certain manipulations to make the computation of the logarithms doable. But at least at this point, we're saying if we're in a neighborhood relatively close to 5, then this will give us a decent approximation. And the idea is that since the logarithm has issues at 0, we can always work around that. There are all kinds of nice adjustments that you can utilize with the logarithm identities to make the convergence a little faster. And so when you've got a really, really nice calculator that has a lot of nice approximation possibilities on it, you pay a little bit more. But now the coding has become so, you know, ubiquitous that you can now go to Walmart and get a really nice calculator for next to nothing. So maybe you didn't spend as much as I thought on your fancy calculator. Certainly when I was a kid, the calculators were not as nice, and we were lucky if they did anything. But my dad was a businessman, and he would give me an old calculator, but it was clunky, and all my friends made fun of it. And I said, well, I don't need it anyway. But it was hilarious. And then, of course, someone would bring in the latest model of calculator, and we were like, oh, wow, look at that. But, you know, I was always like, we got to work it out. We got to work it out. Okay, so now let's look at an example where we look at the remainder. So now you're thinking, well, how does this remainder work for us? So here's a good example from WebAssign. So let's look at this. So it says in this particular example, it says replace, I'll just write it down, replace f of x with the Taylor polynomial. The Taylor polynomial. So we're basically going to have to approximate the remainder, kind of like we do with the integral test remainder and the alternating series test, the first neglected term. That way we get an upper bound. So we just do a little bit of approximation with functions that are halfway nice to us. So replace f with the Taylor polynomial, the third degree. And then it says determine values of x, determine values of x for which the error, and I'm just going to say is less than 1 over 1,000. They say does not exceed, but I think they mean less than 1 over 1,000. That's just a little English, you know, not all mathematicians are English majors, so I can't fault them for that. So, well, what is it? Well, I'll give you the punchline here. And this is one we've already worked on. So f of x, here's what WebAssign gives us. F of x is e to the x. And we're going to be given the Maclaurin third degree polynomial. And we're given the third degree, and you know this, we just computed it. This is 1 plus x squared over 2 plus x cubed over 6. Now, here's a little quirk here. Here, when x is less than 0, okay, we're like, all right, okay, so you're going to make us work a little harder. So the idea is we're thinking we've got 0 here, and we'll probably develop an interval like here, but our approximation is only going to be valuable for the points there less than 0. So basically we have to find an interval so that if we choose any x values here, then the error by replacing f with this polynomial will be less than 1 over 1,000 or 0.001. So this is where I was talking about, you know, we can write down Taylor polynomials and Maclaurin polynomials all day long. And you need to learn how to do that as we've been doing. But we need to know, is this any good? So they must be pretty good because our calculators seem to work very efficiently. So we need to verify this. So first, what we want to do is note that at this point, we must analyze the remainder term. So in this case, what's the remainder term here? Let's just write it down. This is f fourth derivative evaluated at z divided by 4 factorial, in this case times x to the 4th. Where z is between x and the c is 0 and 0. So there'll be a z in here. We're going to try to figure out an x. Again, our approximations were on, you know, this is not a unique deal, but the way these problems are set up is that the approximation will ensue cleanly in only one direction. So you don't have to worry about there being, you know, differences in output, so to speak. So at this point, we know what this is. So let's look at this. So let's look at the absolute value. Then we have 0 less than or equal to the remainder term. kind of like we did with the alternating series test. And so we really do like this function. The e to the x, any derivative is just e to the x. So we get, in this case, e to the z. Because note, the fourth derivative of f is just e to the x. So e to the z, or f, the fourth derivative evaluated at z, is e to the z. And since this is an increasing function, we can bound it at 0. So that's easy. And then we get what? 4 factorial, which is 24, and then x to the 4th. Now, of course, these are all nice positive things here. So we've just got e to the z over 24 times x to the 4th. Now, when you think about the curve here, as this function is increasing, and we're only looking at values to the left of 0, the maximum value will occur at e to the 0. So we're going to say this will be less than or equal to e to the 0, because that'll be the maximum on this interval. So what I'm saying is that when you do these problems, I will give you problems, and WebAssign will give you problems where you can actually do an estimate that's attainable. In some cases, the estimates or this procedure is like not the best. And so when we deal with the binomial theorem, we're going to have to try something else, because this just won't work. I mean, sometimes you just can't get bounds on the derivatives. They're not very user friendly. So we get 24 x to the 4th. Of course, e to the 0 is just what? 1. So this gives us x to the 4th over 24. And we want this to be less than 1 over 1,000. So now we're seeing that when we actually analyze, let me do this, focus. There we go. So when we actually introduce this, is just like we've done in the other problems, like we compute the improper integral and set it less than the desired error, or we look at the first neglected term and then set it less than or equal to. So I mean, the idea, and we don't even have to worry so much about that. We just kind of figure out how far we need to go out so that term is actually pretty small, because the error is that in that case is less than the first neglected term, which is an amazing concept. So now, equivalently, now we've got an easy problem. So we've got x to the 4th is less than 24. So we've got what? Let's see here. We can do 24 over 1,000. So let's see what we get here. This is 4 times 6 over 1,000. So we can divide by 4, and that'll give us 250. And then, of course, now we can divide again by 2 and get a 125, because this is just 2 times 3, right? So we get a 3 over 125. Now, this is just a conjunction. So if and only if we have, let's see, so we're going to look at this as the 4th root. So basically the absolute value to the 4th power. So we're going to get what? X is less than the 4th root. This is what we're going to discard, because we don't really know anything about that, but we do know something about this. Negative 3, 125, 4th root. Then X, so just look at the part that we can believe in. That we get from this, but we don't know anything about that because our bound stopped at 0. So we look at this part. So take X in this interval. So we can write that as we can use the radical, the negative 4th root of 3 over 125 to 0. Now, what's nice about this is that we know that if we select values of X in here, then we're going to be good to have this error, less than this error. And this is probably even much better than this because we've used an upper bound for this. So the thing is that what we have is maybe even better. So the idea is that we could probably cheat a little bit and still be okay. But I actually approximated this with my Google calculator, and you can see that the fourth root of 125, again, this is the binomial theorem, boy, ever, is approximately, I got 0.3936. And that's what you'll see in the lecture notes. But again, you can always just put the exact is the best. If they ask you to approximate, that's fine. You can always try the exact, and if they kick it out, then approximate it. Sometimes the WebAssign is user-friendly. Again, I have trouble trying to convince my pre-cal kids that, 0.25 is equal to 1/4. They think a decimal is always approximation, which I don't know where they learned that. Again, you all are more mature, so feel free to investigate WebAssign, push it to its limits. That's the reason we use it. It's not for the videos, it's for the backbone, the MATLAB backbone. So the computer algebra system is good. So now when we look at this, we see that the Taylor's theorem gives us a way to analyze how good the replacement will be. And so we can see with this type of analysis that if we have a function that does satisfy Taylor's theorem, and that's the thing, it won't work for any function. It has to be a function that satisfies the hypotheses of Taylor's theorem. So we can see that if we want to stretch this more, then we can increase the power of our Taylor polynomial. Okay, so basically what this says is that if you're doing a physics calculation or an engineering problem, you can replace e to the x with this polynomial. Polynomials are simple to work with. They're easy to add, subtract, they're easy to differentiate. And so it's kind of like replacing sine x with x when x is close to 0. Physicists love Taylor and Maclaurin polynomials because you often do nice approximations in physics and engineering when you're doing models. I mean, you have to work it to the point to where you're answering the questions of your clients. So again, this basically shows you how you just take the next level of derivative and then analyze this just like you would have in a previous problem that we've done with infinite series. So this is a nice example in the way of how you would actually approximate. Now let's look at an example where we just kind of have to test values of n. Sometimes this is a nice problem because it's set up very nice. Maybe we can ask a different question. So here, what I want to do is look at an example where maybe we have to figure out the degree of the Taylor polynomial. So here's a good one. Now, this is one that we know about. It's the sine function. So again, we'll be able to do some approximations. I'm not going to give you functions that are going to just, blow you out of the water. There'll be functions that you can actually approximate. And just like we did with the previous one. So here's an example. Let's pick on the sine function. Determine, and sometimes we just have to test values. And so you can always use your Google calculator to see how good a particular number of terms will be for you. So it says determine the degree of the Maclaurin polynomial required for error for error in the approximation to be less than 1/1000. So again, determine the degree of the Maclaurin polynomial required for the error in the approximation to be less than 1/1000. So here we have f of x will be our friend sine x. And what we're asked to do is approximate. Before we had to find an interval for the replacement. Here we want to do is approximate sine of 0.8 or 8/10, which is sine of 4/5. So that's what we want to approximate, 4/5 radians. And we have, we're going to, of course, take c equal to 0 because this is Maclaurin. So again, we think about, what we need to do here. And so this is where we have to do the trial and error bit. So note, we analyze the remainder term. When x equals 4/5. So we know what the value of x is. We just need to see how far out we need to go to get a decent approximation so we can at least know we have 3 decimal place accuracy. So in this case, we use a very remarkable property about the sine function. So note, f of x equals sine x. We observe, which we've used many, many times already in this class, that all powers or all orders of derivatives of sine will be, again, we've got powers of, we just have sines and cosines, pluses and minuses. This will always be bounded above by 1 because these are bounded functions. Before we just used an upper bound on a particular interval that was very convenient for e to the x, and that was nice. So now let's look at the remainder. So now 0, just like we do before, and we're going to have to test the values of n. So this is a trial and error type problem. So remember, this is the n plus first derivative evaluated at z. So here, and we'll with x, and we'll just say, let me add this z between 0 and 4/5, just to kind of remind you about where everything lives, right? So that's the theorem. And then we have what? N plus 1 factorial. And then we have the 4/5. So we fill in this to the n plus 1. So remember the remainder term, as we did for the last one, we have the n plus first derivative evaluated at z divided by n plus 1 factorial. And then of course now we have x minus 0 to the n plus first degree or power, but the x is 4/5 and the c is 0. So we just get 4/5. So now we're like, okay, this is fine. We have an upper bound for all the derivatives, so we can replace that with 1. So this is just 1 times 4/5 to the n plus first derivative divided by n plus 1 factorial. So if you want, you can just go ahead and rewrite this. This will be 4 to the n plus 1. And then we have n plus 1 factorial times 5 to the n plus 1. So this has to be less than 1/1000. So that's kind of where we were with the last problem. So what you want to do in these types of problems, basically you're saying, okay, if I want to use a Maclaurin polynomial to approximate this, and I want this much accuracy. I want 3 decimal place accuracy. Then, you know, within 1/1000, then this has to be satisfied. And this may be even better, okay, because we're using an upper bound here. So this will, the thing is, this may be an improvement. So we know with this case, we can at least get a polynomial that'll give us the required accuracy here. So again, just like the last problem, we're at this point. And so now we just have to test the powers. That is, we can start with, you know, 2, 3, or whatever, and see what we're doing here. So notice, and this is important, when we look at this, if we start out and we like, boom, we're just like, you know, much less than this, we may have to back up some. Okay, we don't want to overshoot it. We just kind of want to get the first one that will work. And so in this case, looking at the powers here, I'm going to start out with n equal 3 and test. So basically what we want to do is test values of n, or degrees of the polynomial. So we'll take n equal 3. So this is all we can do. We're just like, okay, well, let's just see what this gives us. So this will be 4, in this case, to the 3 plus 1. And then we have 3 plus 1. So this is 4 factorial. And then 5 to the 3 plus 1. So this is 4 to the 4th. And we have 4 factorial, so that's 24, times 5, in this case, to the 4th. So now with the, here, if you like, this will be 4 times 4 times 16. And here we just have what, 3 times 8 times 5 to the 4th. And so now notice here we got, we'll kill 8 out of here and left with a 2. So this will be 2 times 16, and then 3 times 5 to the 4th. So that'll give us 32. And then we have 3, and that's just going to be 25 times 25. So that's 625. So this will give us 32. And then we have 3, so that's 1800 plus 75, so 1875. But that's too big. This is too big. That's not less than 1/1000. This is too big. Now, if you want to check your Google calculator, you can, but you can see that's too big. So that won't work. Okay. So let's try another one. Let's try n equal 4. So now we can move it along a little bit quicker. So when we have 4, we're going to get 4 to the 5th. Just use our recipe here, 4 to the 5th. And then we have 5 factorial. And then 5 to the 5th. So in this case, we don't have much. I mean, we've got some stuff in here. So if you want to reduce some of this, you can. So this will be a 5 times a 4 times a 3 times a 2, and then 5 to the 5th. And here we've got what? We've got a 4 times a 4 times 4 to the 3rd. And so here we can see that the 8 will absorb and leave a 2 behind from that 16. So we get a 2 times 4 to the 3rd. The 8's gone, and we're left with a 3, 3, and then an additional copy of 5, 5 to the 6th. So that's a 64. So this is a 128 divided by 3 times 5 to the 6th. Now I tested this value with my Google calculator, and this is approximately 0027. Again, this is too big. So that's not going to work either. So I think you can see here that we'll probably get the jackpot with n equal 5. So basically all you have to do is test here. This is trial and error. We can't really do any better than this because this is not a function that, of course, if you're doing a numerical analysis problem, you can just run a little routine to check it, an if then statement, and boom, you're done. But we have to do this by hand. So now we have 4 to the 6. So n is equal to 5. So we get 6. And so now we have 6 factorial. 5 plus 1 is 6. And now we have 5 to the 6. So here, same old song and dance. So 4 to the 6. So let's just do this. Keep it simple. 6 times 5 times 4 times 3 times 2, all times 5 to the 6. And then, of course, the same thing going on here. We got a 4 times a 4 times a 4 times 4 cubed. So now notice here the 8's going to go. So that 8 is going to be gone. And then we're going to have another 2 in here. So this will be a 2 times a 3. So we've got a 16. So all of that's gone. That 16's gone, but it leaves the 4 behind. So we get 4 to the 4. And then we're left with the 3, 2 copies of 3, and the 5. So we got 3 squared, and then a 5 to the 7. So now we've got 5 to the 7 here times a 9. So 4 to the 4, 9 times 5 to the 7. And this is approximately, this is good enough, 0.000364. And this is good because this will preserve the 3 decimals. That is, this is smaller than 1 over 1,000. So all of these were too big. So this is the first case where this is actually true. So we say true, not, symbolic calculation is a good thing, ladies and gentlemen, because here this is quick, but you have to understand Taylor's theorem to do this. You can say, well, let's just take n equal to 8 or something. That'll work, but I want you to practice this and get the first one for which it works. For instance, if you got a nice fancy computer and you're thinking, let me just run it out degree 10, I'll be fine with that, I'm sure of it. Well, that's probably true. But at this point, you're thinking, okay, so so we'll say P5 of X is sufficient. So now when you think about this, what is this saying? What is this saying? Let's check it out. I mean, let's do some due diligence here. Maybe Taylor sold us a bogus bill of goods. So now we say P of 5, remember what that is? P of 5 is X minus X cubed over 6 plus X to the 5th over 120. So we can use this as an approximation. That is, if we use our Google calculator, we can take P5 of 4/5, and that will be our error less than 1 over 1,000. So now we can see that P5 of 4/5, which equals 4/5, this is how your calculator works. 1/6, 4/5 cubed plus 1 over 120, 4/5 to the 5th, has error less than 1 over 1,000. And it's probably even better than that. We know we have that, it might even be better. So now you can see the arithmetic capabilities here of Taylor's theorem. That now when we talk about using technology to compute logarithms, using technology to compute values of trig functions that we don't know exactly from the unit circle or from using some convenient identities. Like for instance, we could write down the exact value of the cosine of 75 degrees using sum formula easily, or a half angle formula, get it exactly. But if we don't have that, we have something like 4/5 radians. So the beauty is that this again shows you the arithmetic nature of the calculus, and that when we do examples, we're basically doing the sophisticated arithmetic. So when you do these, just test them out. You know, go to your Google calculator and test it out and compare it to what they produce for the actual sine function. And so you can see that the error is preserved, that we do have an excellent approximation. So this may be more than enough. Maybe you're doing a physics calculation and this will give you more than enough accuracy. You're doing a problem in engineering, this will give you more than enough accuracy. So the idea here is that the polynomials make all of these transcendental functions, which are abstract from the get-go, very unabstract, okay? So let's look at an example where we look at a function that seems fairly tame and we want to do the same thing. And then what we'll do next week, we'll start with the power series. I wanted to spend a little bit more time with this. Yesterday I thought about it and I said, well, they don't need to see this. And then I thought to myself, you do need to see this. You need to understand this. So let's do the same technique here for a simpler function that later when we do this, we're going to figure out how we can work this through the geometric series. So again, let's do the same thing to get some practice with it. So here, determine. Now, the only way this works, ladies and gentlemen, is if we can come up with some way to characterize the nth derivative. If we can't, we're cooked. And then we do what we do is just make n really large and keep our fingers crossed, which isn't best. That's not going to impress your boss. So determine the degree of the Maclaurin polynomial the degree of the Maclaurin polynomial required for error, excuse me, less than, in this case, 1 over 100. Now, what we're going to try to do is figure out a pattern, and you're going to see the pattern. So we're going to have f of x. This is actually geometric, which you can see from the very beginning. 1 over x plus 1. And what we want to do is approximate. These are really good examples. Dr. Larson has written an excellent book. He throws the calculator in there too much to keep all the publishers happy, but his book is good. So approximate 2/10 or 1/f of 1/5. Okay, and you're thinking, well, you know, Professor Ron, I just plug that in and I'm done. I can give you the exact answer. Okay, that's not the point here. I mean, you're like, well, that's easy to do. I agree with you, but that's not the point. I want you to get some practice with this. So basically what we want to do is develop a general formula. Develop a general formula for the derivative. I mean, you know, I wanted to mention the fact that you can do this directly and get the exact answer, but I want you to get some practice with this because there may be cases where you need to replace this with a polynomial. So here's what we do. So we have n, and we're going to look to see what happens with the derivative. So let's just do f n of x, and let's do. I think we can do several of these and figure out a nice pattern. So now what we want to do, again, we have x is equal to 1/5 and z between 0 and 1/5 from Taylor's polynomial. So this will be what, x plus 1, to the negative 1. And this is what you did in Cal 1. So we're going back to that. So again, here we're going to have what? Negative, in this case, x plus 1 to the negative 2. So we're going to get a factorial clearly. And here the 2 will come down the negative and absorb that. So we have 2x plus 1 to the negative 3. Don't we wish we would have had that in the theorem for Taylor's theorem proved? No negative sign. And then we get a negative 6x plus 1 to the negative 4. And then, of course, we get a 24x plus 1 to the negative 5. So now what we can see is we have a general formulation. This is inductive. So we see the nth derivative. We're going to have the power of 5, one more than the order of the derivative, and then we're going to have the n factorial, and then the alternation in sign. So we can do negative 1, and in this case we want the first one here to actually be positive. So what we can do is just start out with n. So negative 1 to the 0 by definition is 1, and then when we put in 1, we'll get the negative. So the n will suffice here. And then, of course, it looks like we're developing the n factorial. And then downstairs, we have the power of x plus 1 that is one more than that of the order of the derivative. So this is just a good little exercise, very simple though. Okay. So now what we want to do here is look at the actual remainder term. So here's what the derivative looks like. So now consider the remainder. I'll write down what this is. This will be the n plus first derivative evaluated at z divided by n plus 1 factorial times x to the n plus 1. Again, c is 0, so c equals 0, as you see there. So now for the n plus 1 derivative, we'll just replace all of these n's with n plus 1. So we get what? Negative 1 to the n plus 1, n plus 1 factorial, and here, sorry about that, this is correct. I'm going to have to put my n plus 1 or n plus 1 factorial down here. So we get what? X plus 1 to the n plus 2. And then we have, let's see, and then I'll fill in all the x's. And then let's see, we've got what? The n plus 1 here. Now let's fill in the x's. So we have negative 1, n plus 1, n plus 1 factorial. And then we have 1/5. So in this case, we've got, and here, oh man, sorry about this. Notice here, this is a z. So that's a z there. And then we have the n plus 1 here. And let's see, and then we've got this, and we've got this. They are going to absorb. And let me go ahead and put in the value of x to save a little bit of time. So now I can get rid of this. So let me recap what I have here. We've got the n plus first derivative evaluated at z So here we've got -1 to the n plus 1 times n plus 1 factorial, just replacing n with n plus 1. And then we have the z, where the x goes, z plus 1 to the n plus 2, and then the n plus 1 factorial here, and then the x, which is 1/5 to the n plus 1. And now what we're seeing here, and this is what makes this problem a little bit simpler, is that now when we reduce this, the n plus 1 factorials go away. And also, let me make sure I've got all of this in good stead. So this is an n plus 1, which I have goes to n plus 2, and then we have the n plus 1, and then we have the n plus 1 factorial, and then this n plus 1. That looks good. So these go away. So we get -1 to the n plus 1 over z plus 1 to the n plus 2. The n plus 1 factorials go away, and then we have 1/5 to the n plus 1. Now, this is where we see that everything goes away, because this will just be an upper bound. That is, this is between 0 and 1/5. And so what we can do here is make this as small as possible. So we're going to move this to be the 0. So if we replace this with the smallest value of c that it could be, then this will be the largest that it can be. So this will be less than or equal to, again now, -1 to the n plus 1 over 1 to the n plus 2 times 1/5 to the n plus 1. And this is just 1. So we get 1/5 to the n plus 1. So now this is what I was talking about. The derivative is easy, but it's a little bit more complicated, because when we go to the n plus first derivative, we've got to make the correction replacing n with n plus 1. And then, of course, the n plus 1's absorb here and here. And so we're left with this simple thing. And this must be less than 1 over 100. So now we can test. So let's do a test. So first, let's look at n equal to 1. So in this case, we have 1/5 to the 1 plus 1, which is 1 over 25. That's too big. And so now we look at n equal 2. So we have 1/5 to the 2 plus 1, which is 1 over 125. And that's actually fine. This is less than 1 over 100, and this is good. So in this case, therefore, n equal 2 is sufficient. Which implies P2 of x gives the proper degree of accuracy. Now you're thinking, again, this is a hard problem, and you can just go ahead and plug in the value and know what it is. But this is important. This is why I wanted to go through this. Let me kind of rephrase everything that I've done, because I worked this a little bit differently than I had in my mind. We come up with a formula for in this particular case, for the actual value of the derivative. That is, we see that the factorials fall right out of here. And then we say, okay, well, we have an alternation in sign. We have the development of a factorial, and then the power of x minus 1 in the denominator that's 1 more than the order of the derivative. And so when we write down the remainder theorem, we have to substitute all of that in. Now, of course, this is for z between 0 and 1/5. So we have f to the n plus first derivative evaluated at z divided by n plus 1 factorial times x to the n plus 1. That's the definition that we have come up with, or the actual formula for the remainder. And so now we fill in the derivative, that is the n plus first derivative. So this is -1 to the n plus 1 factorial, and then we have z plus 1 to the n plus 2, and then here we have the n plus 1 factorial from Taylor's theorem, and then x, which is 1/5 to the n plus 1 power. Now when we look at this and we think, okay, well, let's just see what we have here. We need an upper bound for this. That is, the n plus 1 factorials absorb, and we're left with this. And then we're saying, how big can this be? Well, the smallest that this can be will make this larger. So we just replace z with 0, the lower bound here. And then we get a simple upper bound. That is, this is as large as it can be, but this is just the absolute value of -1 or +1, which is 1. And we're left with 1/5 to the n plus 1. And so now that's it. And that has to be less than what? 1/100. This is an excellent example. I love this example. You need to know how to do this. So now we have n equal 1. So we just say, all right, trial and error. We put in 1, we get 1/25, clearly too big. So we try n equal 2. We get 1/5, 2 plus 1. So that'll give us 1/125. Of course, this is smaller because the denominator is bigger, just the opposite of what we used here. And so this is good. So now we see n equal 2 is sufficient to give the desired degree of accuracy. So now, what does this say? Let's just write it down. And we'll be done with this. So now, let me write down what this actual polynomial is. So we have P2 of x. And so at x equals 0, let's just go ahead and put in, stay with me on this. I want you to see this done. So let's just go ahead now and put in the 0. Since we're going to do this extra little bit, this will just be a 1. This will be what? A -1. And this will be, well, and then we get what? 2 here. Put in 0, we get 2. So this is all we need for P2. So now we get f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared. So that gives us a 1, and then plus, so minus, so the next one is a -1. So we get minus x, and then we get plus, so the next one we have a 2, and the 2 factorial here. So we have 2 over 2 factorial times x squared. So this is 1 minus x plus x squared. That's the degree 2 Taylor polynomial, and P2 of 1/5 is correct to 2 decimals. So what's interesting about this is that if you think about it, let's just look at it. Let's just compute it. It's simple enough. So we get 1 minus 1/5 plus 1/25. So you get a 25. So we get a 25. 5 here, that'll be minus a 5 plus a 1. So this will give us a what? In this case, we've got a 21/25. Now, if we just substitute, that is f of 1/5 is just 1/1/5 plus 1. and this is 1, so this will give us a 5, so a 6 over 5, 5 over 6. So that's the exact, and that's the approximation, not half bad. So the idea is that what we're seeing here, you're saying, oh, wait a minute, Professor Ron, that's geometric. That's a geometric series. Well, that's not a surprise. The idea here is that we could construct this with the sum of the geometric series, but we know that what I've told you is that every Taylor series is going to be its, every convergent power series is going to be its Taylor series. So if we did this a different way, it would still coincide with this. So we get something we expect, okay? So the beauty of Taylor's theorem is that you can do problems you already know how to do, but then you can extend it to problems that are more abstract, like e to the x, ln of x, sine of x, cosine of x, etc. So make sure that you take time to go over this, that you take time to, where was that sine problem? Right here. These are very similar in nature. This one, this example with the sine, and then of course the example with the e to the x. So what we're seeing again, the key in doing the Taylor's theorem is being able to analyze the remainder. The remainder is the key here because it tells us how good is our approximation. So what I keep doing is I'll say, okay, now go back and read this theorem again. That's exactly what we're using, but we see that analysis of this does keep us on our toes. For instance, when you start to substitute, and like I say, when you do these approximations, there are always going to be ones that you can do. I'm not going to give you examples where this is overly difficult. It'll be a problem where the derivative is generated cleanly and you can get an upper bound without too much effort. So I hope that you're enjoying this. Now, what are we going to do after this? Sorry, I've been long-winded, but when I worked through this problem, I changed what I wanted to do with it, and I like what I did. I think this is nicer. Getting the general formula is a cleaner way to do it. But what we're going to do is we're going to take these polynomials here, and we're going to extend them. We're going to look at general power series. And we're going to say, okay, if we've got these infinite series of power functions, just like these are power functions, how are we going to figure out where they converge? For instance, when we think about this problem here, it's going to be similar to what we did with the example of the exponential. Let's see, where did I put that? I'll find it. Oh, yeah, right here. So we're thinking we're going to look at something like this where we're like, okay, this took a little bit of work. Is there a way to streamline this? That is, if I give you just a regular power series, we need to figure out how we can find the interval of convergence. And what we're doing here, it's going to be symmetric. So we need to do that and generalize that. And once we do that, we're going to go back to the power series and represent them using techniques with the geometric series. And then in the last section, pull all of this Taylor polynomial into the infinite case and see how it is all the same. And then we'll have a list of standard power series that we can use to do other calculations. So I spent more time on this, ladies and gentlemen, because this material is extremely important. This material is what you need to really spend a lot of time on because it will pay off handsomely with what's left in the course. So I appreciate you all sticking around a little bit extra time for this. Again, remember what's left in your calculus sequence and differential equations, and some of you will take partial differential equations. The infinite series are key to that understanding. So please spend some time on this and make sure that this is something that you're comfortable with. I've done a lot of examples and I've given you plenty of theory to make this realizable. So thanks for your patience today. I'll I'm not going to promise that I'm not going to go over in the future, because I probably will. But everybody have a good day. Stay warm. And if I don't see you at the conference hours, I'll see you next week, and I'll get up some of the posting of grades, especially with the test and the signature assignments. So everybody have a good day.